Hey everybody, welcome back. It's Mr. G again. So we're back doing another lecture for the Electric Machines class, ELIC 200. So what we're going to be doing today is our topic is going to be on power calculations. So in the previous video, what we've done is looked at power generation. Now we're going to start looking at calculations using power, so based on power. So in order to do that, we need to do a few things. We need to figure out what is active power, reactive power, apparent power, what is the power factor. We're going to go through some basic power formulas. And then we're going to look at something known as the power triangle and the phase angle of a circuit. So that's what we're going to be looking at today. So let's get started. So the first one we're going to look at is active power. So in an AC or complex system, there are three types of powers. There's active, reactive, and apparent power. Active power is the power that actually does the work. So it's power that does the work. It is power that is dissipated in resistive loads. Because it's in resistive loads, voltage and current are in phase. There is also no negative power. So if you remember from last week's lecture, when we had the power generation and we had a voltage and we had a current. When we looked at the power waveform looked like this. So there's no negative content in that power waveform. The unit is the watt, and the symbol for watt is W. The symbol is the letter P for power. In some books, we'll see different symbols that are being used, but in our case right now, and what we use in our textbook, is the letter P. And I'll talk about some of the other symbols as we go along. So, if we looked at the characteristics for active power, so active power is found in resistive loads. It does the work. The voltage and the current are in phase. There's no negative power. The unit for active power is the watt, and the symbol is the P. When we looked at calculating it, power is equal to voltage times current, and that would be active current. So current that is in the resistive part of the load. Sometimes active power is referred to as real power or true power. In our class, we refer to it as its real term, which is active power. Next up, we have reactive power. Reactive power is typically found in reactive loads. So reactive loads are capacitors, and inductors. As you know from AC circuits, when we're dealing with capacitors and inductors in the AC world, we have a phase shift. So, reactive power, voltage, and current are out of phase. So therefore, we end up with some negative power. Negative power refers to power that travels from the load back to the source and then gets sent back again. So reactive power is actually referred to as imaginary power. This power does no work. So, reactive power, sometimes referred to as imaginary, has a negative component to it, so that means that power is sent back from the actual load to the power supply. Because remember, negative in electronics means opposite direction. It doesn't mean less than zero. So with negative power, we end up sending power back. It does not do work, so it's not the power that actually does work in a load. It is not dissipated. It is just flowing back and forth from the supply to the load. It does not actually do any work at all. The unit is the VAR. That stands for volt amp reactive. Again, the unit VAR, volt amp reactive. The symbol is Q. In some books, you will see P and reactive. But in our book, it is Q. So we will be using Q in this course. That is the symbol. The formula for calculating Q is equal to E times I of Q. So that means the current flowing in the reactive part of the load. So we have reactive power, which is found in reactive loads, so that's capacitors and inductors. In the AC world, voltage and current are out of phase in these components, so when we do our multiplication, we end up with some negative power. So we have imaginary power that does no work. The unit is the var. The symbol is Q, and the formula is E times I of Q. So again, that's the current that's flowing in the reactive part of the load. The last one is apparent power. Apparent power is the vector sum of active and reactive power. So it's the vector sum, so it takes into account phase angles. So basically, the symbol is S. The unit is the volt amp. The formula for S is equal to E times I. This I represents the total current flowing in the circuit. So that means the current that is flowing in the resistive part as well as the current flowing in the reactive part. So the total current flowing times the voltage, and that's what we get for apparent power. So it's the vector sum of active and reactive power. So it takes into account the actual angles, the phase angles of the system. So when we look at it, S is equal to the square root of P squared plus Q squared. In some books, you will see it as PA, apparent power. But again, we are going to be using the symbol S. That's the way our textbook uses. So everything in this course, we're going to deal the way the textbook does. So apparent power is S. The unit is the volt amp. All right. Power triangle. Power triangle is a visual representation of the vectors that represent the three types of power. So again, the three types of power, we have P, which is active. We have Q, which is reactive. And then we have S, which is apparent. So, when we look at the power triangle is a visual representation of P versus Q versus S. And what we end up with is a phase angle between them all. So this is the way it works. Active power, because active power is real power, true power found in resistive loads, active power is on the x-axis. Reactive power is found on the y-axis. Now, hopefully you can recall from AC circuits that if we are dealing with a capacitor, it is different than dealing with an inductor. So for powers, the capacitive phasor goes down and the inductive phasor is up. So when we're dealing with the powers, the capacitive power, the Q, is the negative side of J, and the QL is on the positive side. So basically S, which is apparent power, is the vector sum. So let's pretend for an example, we had some Q inductive and we had some active power, so reactive from an inductor, and some active power. The vector sum of the two is the apparent power in the system. And this is where we get the phase angle. So this would be if we have an inductor in our system. If we have a capacitor in our system, it looks like this. So here is the P, here is the Q, the vector sum of those two is S, and here is my angle. So the angle is basically between P and S. That's our angle. How do we calculate the angle? So the angle in both cases is calculated. So the angle is tan minus 1 of Q over P. So that's how we would calculate the angle. Since this is a right angle, we can use our trig laws it's tan minus 1 of Q over P gives us the phase angle. Now, the phase angle in this case will be positive, in this case will be negative. If you know that it's a capacitive load, it will be a negative phase angle. If you know it's an inductive load, it will become a positive phase angle. So, just for the calculation point, here I have a positive going Q, so let's say Q here is plus 14. It's positive going. P is 35. Therefore, what is the phase angle? So if we go to our trusty calculator, 14 divided by 35 equals, and tan minus 1, so that is a phase angle of positive 21.8 degrees. If we do this side, we know that we have a negative going Q. So let's say Q is going to be negative 14. P again, 35. So we're looking for the phase angle. So bring up the trusty calculator, 14 on the negative side divided by 35. And we have a negative phase angle. So we end up with minus 21.8 degrees. So, if we're dealing with inductors, we have a plus Q. If we're dealing with capacitors, it's a negative going Q. Will give us a positive going phase angle or a negative going phase angle. So in our power triangle, QC is down below, QL is up above, and P is on the x-axis. And the vector sum becomes the apparent. That's why if you go back just a couple of minutes, Pythagorean's theorem, S is the square root of P squared plus Q squared. So Pythagorean's theorem, Y, because these are right-angled triangles, and Pythagorean's theorem calculates. So based on these values in Pythagorean's theorem, we can calculate apparent power. And then we have this other formula here that will calculate the phase angle for us. And then we get the vector representation of power. So that's what the power triangle helps us figure out. It is again a vector representation. All right, what about currents in the system? When we're dealing with active and reactive powers, remember we had IP as active current, IQ as reactive current, and I as the total current flowing through the whole system. How do these values calculate? Well, if we looked at the vector system for current, if you remember from AC circuits, again, the current in a resistive load, so IP is on the x-axis. Then we have IQ or an IQ, depending on whether or not we were dealing with inductive or capacitive current. If you remember from AC circuits, IQ, this one is leading. Okay, so this one is leading this one by 90 degrees. So that makes this capacitive current. This one is lagging here. This is a lag. So this makes this the inductive current. So whether or not you have a capacitor or an inductor, your current will either be on the positive side of J or the negative side of J. And again, our current in the active component is on the x-axis. If we looked at where our voltage would be, our voltage would also be on the x-axis. Our voltage is on the x-axis because voltage and current in a resistor are in phase. Current in a capacitor leads the voltage by 90 degrees. The current in an inductor has a 90-degree lag from the voltage. So the way I like to think about it is if I'm going in a circle like this, in that direction, so a clockwise circle, I run into this before I run into this. So this one is leading. It's ahead of this by 90 degrees. Then, after I pass this one, I then hit this one. So this one lags behind by 90 degrees. So this current leads the voltage. This current lags behind the voltage. So where does this current end up? Well, we have the exact same thing as what we did with the power. If we had IQ of a capacitor, and we had active current, when we did the vector sum, this would give us I of the circuit and a phase angle. If this was IQ of an inductor, IP of the circuit. The vector sum is going to be I of the full circuit with a phase angle. Calculating that phase angle, again, the phase angle is equal to tan minus 1 of IQ over IP. So calculating the phase angle, again, it's the same formula. So when we look at current, the vector representation of the currents looks like this. And depending on whether we have capacitive current or we have inductive current, will determine whether or not our phase angle is positive or our phase angle is negative. All right, so we have something known as power factor. Power factor is a representation of how much power is doing work with respect to how much power is being sent to your system. So, as an example, we have, if we did a bunch of calculations on, let's say, a machine in a factory. If the machine had a motor in it, we would have Q. We would have P if that motor was doing some work. And together, we end up with apparent power. So, we know that apparent power is made up of the voltage that is sent and the full current that is sent. So if we were to examine a motor in a factory, so we've got a machine and there's a motor in the factory. So we've got a voltage that is being sent by the hydro company. That motor has P and Q because the motor itself is an inductive load. It also has resistance, so therefore there's some P and there's some Q. So therefore the current that is actually flowing to that machine is I. So we know that because we have a P and because we have a Q, that translates to an S, apparent power. And we know that apparent power is the voltage that's supplied multiplied by all of the current. Now that current is made up, remember, of the vector sum of this current and that current. So the active and reactive currents. But together, this is what's being sent by the electric company. They're providing a voltage and they're providing current. What we want to know is how much of this electricity is actually being used to do work in that motor. You have to remember back from a few minutes ago when we looked at the difference between active and reactive power. Active power does the work. Reactive power does no work. So, active power is the part that's doing the work. reactive power is doing no work. So, as a company, we want to know how much of the total electricity that's being sent is actually doing work and how much is not. Power factor is a ratio. So power factor is a ratio of P over S. So, how much of the total is actually doing work? That's what power factor is. It's normally given as a decimal point. So if I took an example and I said 800 watts is doing work over 1,000 volt amps. So the hydro company is providing 1,000 volt amps for this machine, and 800 watts of it is actually being used to do work. Therefore, the power factor is 0.8. Sometimes it is also represented as a percentage, so therefore that would be 80%. So 80% of the total electricity that's making it to the machine is actually doing work for us, and the rest is not. So the 20% is wasted. So power factor, again, is a ratio of how much energy or power is doing work over how much is actually being sent. So how much of the total is actually doing work for us? So power factor, if you remember from just a moment or two ago, if we looked at our power triangle, so if we looked at our power triangle, there's a relationship between the length of this one and the length of this one. That's power factor. So how much is doing work over how much is sent? So that is power factor. If you notice, we also have P and Q separated by a phase angle. So P and Q separated by a phase angle. So we can actually use that in calculation. The phase angle is the cosine -1 of the power factor. So let's just do our little example here. Q was 14, P was 35. What's S? So if we go back into our math, we know that S is equal to the square root of P squared plus Q squared. So in this example, let's calculate S. So P is 35, squared plus 14 squared equals and square root. So in this example, S is 37.7 volt amps. One thing you will notice, it has to be true, is that S has to be bigger than either of these. Okay? It cannot be smaller than any of those. If Q was 0, then S is equal to P. But there's no way that we can have an S that is smaller than any of those two individuals. So, if we looked at the power factor now, so in this case, power factor is 35 divided by 37.7 equals. So a power factor of 92.8%. So a power factor, in this case, was 92.8%. So if we looked at this, all right, so our power factor worked out to be, in this example, 92.8%. We're going to apply this formula and come up again with our angle. So we've got 0.928 and 21.8 degrees. Same, 21.8 degrees. So using this formula here, we can also calculate the phase angle in our system. So what we've got is some calculations based on active power, reactive power, apparent power, something called the power factor. We had a couple of formulas tossed in there, and the power triangle and how that relates to the phase angle of our system. Okay, so again, active power, reactive power, apparent power, and then some calculations based on power factor, current, and the power triangle. So, I hope this helps. Until next time, everybody stay safe, and we'll see you again. Take care.